Alright, here we see question number 6 from the 2013 exam, and we're going to answer the following questions using principles of molecular structure and intermolecular forces. So we see two compounds with the same empirical formula, so these must be structural isomers. So they've got the same mass, so they would have the same LDFs as far as mass is concerned, but maybe by structure they could have different LDFs, whether or not one is more polarizable. That's something to think about. I see an oxygen in there, so we could potentially have some oxygen-hydrogen bonds leading to hydrogen bonding. Something else to think about. And carbon and oxygen is a polar bond, whereas carbon-hydrogen bonds are nonpolar. So these are all things that should be flowing through your brain when you see this. And then we see solubility in water and boiling point. And our first compound, slightly soluble, low boiling point. Second compound, soluble, high boiling point. Ding, 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 ding. Compound 2 has greater intermolecular forces and must have intermolecular forces more similar to water because it is soluble. Alright, so now let's jump into our questions. Compounds 1 and 2 in the data table above, same empirical formula, different physical properties, got that. The skeletal structure for one of the two compounds is shown below in box X. Complete the Lewis electron dot diagram of the molecule in box X, including any lone non-bonding pairs of electrons. Well, first of all, C2H6O, that is 20 valence electrons. So they've already put that there. I know I can only have single bonds with every hydrogen. So if I put all the single bonds with the hydrogens and single bonds everywhere else, that's 1, 2, 3, 4, 5, 6, 7, that's 8 bonds. 8 times 2 is 16 electrons already. And we know that oxygen needs 8 electrons, and typically when it's only single bonded, has the lone pairs. That adds up to 20. That is our Lewis electron dot diagram for that structure. So that looks good. Part 2 now says in box Y, draw the Lewis electron dot diagram for the other compound, a structural isomer. Well, I can't do anything different with hydrogens. They can only single bond. So I think the only logical thing is to move this oxygen from here in between the two carbons. And when I do that and keep the lone pairs, now I have my second structure. I don't think we wanted to add any double bonds or anything, because there would, if you could mess around with that, but there's really nothing else to do with all those hydrogens that can only single bond. And now hopefully you notice, this right here is hydrogen eligible for hydrogen bonding. This is not. All the hydrogens are on carbons, so those are all nonpolar. I do have potential dipole interactions here, but no hydrogen bonding. And so now it says, on the basis of the complete diagrams we drew and the information in the data table, which I brought down here, which compound, 1 or 2, has the structure represented in box X? And again, box X shows us hydrogen bonding. Justify our answer in terms of intermolecular forces present in each compound. So I got to mention both compounds. So box X is going to be compound 2 because it's soluble in water and has the higher boiling point. So compound 2 is in box X. It can form hydrogen bonds between molecules. Make sure you mention that. It's forming hydrogen bonds between the molecules. That accounts for its higher melting point. Oh, sorry, that should say boiling. Higher boiling point. And being more soluble in water, because water also experiences hydrogen bonding. And so that's what makes, when you've got the two compounds with similar IMFs, that's what makes them miscible. And then again, it said justify based on forces in each compound, unlike compound 1, which has weaker LDFs and dipole-dipole IMFs. does not have the ability to hydrogen bond, but it did want us to mention the intermolecular forces present in both compounds. Now, compound 2, you could also mention the LDFs and the dipole-dipole, but the key is that it can form hydrogen bonds. That gives it a higher boiling point. That makes it more miscible with water. Alright, so now part C and D. Here I have dichloromethane and carbon tetrachloride. I see carbon-hydrogen bonds, which are nonpolar. The carbon-chlorine bond is polar. But then you should also start to notice, there's 2 of them here versus 4 here. And hopefully you remember, carbon tetrachloride, that was one of our, yes, there's polar bonds, but the molecular geometry, they all cancel out. The tetrahedral formation makes that a non-polar molecule. Again, hopefully some things that are floating through your head. Notice the boiling points, dichloromethane lower, and has a higher vapor pressure. So you have to look at the data and answer the questions based on the data. So it says dichloromethane has a greater solubility in water than carbon tetrachloride. Okay, so dichloromethane is more soluble in water. Remember what that means. Its IMFs have to be more similar than the carbon tetrachloride. And again, account for this observation in terms of the intermolecular forces between each of the solutes in water. So I have to mention not only dichloromethane, but also carbon tetrachloride. So my dichloromethane, CH2Cl2, is a polar molecule. Carbon tetrachloride is nonpolar. Therefore, the CH2Cl2 has IMFs that are more similar to water, dipole-dipole interactions and LDFs, compared to carbon tetrachloride, which only has LDFs, giving it a greater solubility. We don't say like dissolves like. That's a nice phrase, but that's not evidence-based. Okay, we need to mention the IMFs because that's what makes things soluble in water. Things that have IMFs more similar. Now part D, in terms of intermolecular forces, why does dichloromethane have a higher vapor pressure than carbon tetrachloride? So, while they might not be similar to water, these IMFs in carbon tetrachloride must be greater than dichloromethane. Because think about it, the IMFs are holding the liquid molecules together, not allowing them to vaporize. So the carbon tetrachloride has a very low vapor pressure because those IMFs are holding the liquid together, hold it together. Compared to dichloromethane, which even though they're similar to water and allows it to be soluble, they must be weaker because many more dichloromethane molecules are escaping to the vapor phase, giving it a high vapor pressure. So the dichloromethane has the higher vapor pressure, therefore the London dispersion forces in carbon tetrachloride must be stronger than the IMFs in dichloromethane. It's proven by the data. 89 versus 353, that's a big difference in vapor pressure. So the carbon tetrachloride LDFs must be stronger, holding them together in the liquid phase. And now the last part here, the complete Lewis electron dot diagram of methanol, formaldehyde, is shown in the box below. Molecules of methanol can form hydrogen bonds with water. Draw a water molecule in a correct orientation to illustrate a hydrogen bond between a molecule of water and the molecule of methanol. Use a dashed line to represent the hydrogen bond. Give them what they want. One water molecule, correct orientation, dashed line for the hydrogen bond. Now the thing you got to be careful with here is that the dashed line must attach to the lone pair on the oxygen and must come from the hydrogen of the water. The hydrogen is partially positive, the lone pair on the oxygen is negative. Some people accidentally connect the lone pairs, and that's not right. Don't connect the oxygens. The hydrogen from the water is positive. That dashed line must go to the lone pair. Alright, I hope this helps. See you soon.